So, please, good morning to everybody. Welcome to the webinar, Synchronized Waveform Measurement of Application in Power Systems, that is going to be delivered by Farnoosh, Rahmatian. First, I want to thank to the audience. We are proud to have people in this webinar from 13 countries. To our English-Spanish translator, Maria Sainz, please notice that the participants can select the audio channel to hear, Spanish, English, as you want. Thanks to the Power Department of the Republic University to the multimedia support of this webinar, to the IEEE for the general support, but also especially with the event tools that we have in the organization, to Santiago Leon from IEEE PES&IM coordinator who introduced me, Dr. Rahmatian, and finally to Dr. Rahmatian to sharing his knowledge with us. Dr. Rahmatian has contributed to several techniques for power systems, measurements, and automation over the past 30 years. He is a fellow of the IEEE for contribution to optical voltage and current sensors. He is a past chair of the IEEE PES Technical Council and active at several committees. He is also active at CIGRI, where he is a distinguished member, IEC, and NASPI. Dr. Rahmatian has over 100 technical papers and 12 patents of the credit. At the end of the presentation, we are going to have some time for questions and so on. Please use the chat writing in Spanish or English, perhaps also talking, but as you want. So, Dr. Rahmatian, the floor is yours.
Thank you for that kind introduction. For everybody else's comfort, I usually just go by Farnoosh, so thank you for that kind, but either way is fine. Let me get this slides on, sharing my screen. Just a second. Oh, sharing the whole screen. Y'all can see my screen?
Yes.
Okay, good. And I put it in presentation mode. Actually, hold on. Oh, is this good?
Yes. Okay. Excellent.
Okay, well, we'll talk a little bit about synchronized waveform measurements and some applications, and maybe a couple of even examples in this presentation. I just want to acknowledge some of my collaborators. Together, we had a panel at the IEEE PES general meeting. Most of the material here is from my presentation, but I do have a little bit from my colleagues, particularly Dr. Mohsen and Rod, and they have kindly agreed to share that to make this presentation a bit broader and richer for the audience, and I'd like to thank them. This is a little bit outline. I'll go back a little bit to basics of voltage and current measurement in power system. I know everybody has different backgrounds, some that may be boring for them because they're extremely familiar with it, and some may find a little bit of insight in it. Go a little bit through a definition per se, so that we all are on the same page on what we mean by synchronized waveforms. And then we look at a bit of the application, data quality considerations, and the more interesting part of all of that is some examples. Just as a matter of definition, by synchronized, we really mean time tagged, meaning when a waveform arrives, we know exactly to microsecond exactly when it was taken. So the event on the grid that we have the voltage or current waveform for, what is the timelines? That's what we mean. That allows being able to compare different waveforms from different times together. That's sort of the basic way we look at synchronized. Now, this could be synchronized and could be real-time data, could be delayed data, could be historical data, meaning data that was taken a long time ago when people look at it. And a lot of you may be familiar with synchrophasers. So I want to distinguish between synchrophasers and synchro waveforms. Phasers are in a way an abstraction or a compression, if you like, data compression, when the signal is very nicely behaved single sinusoid type signal that can be described by this equation. X of t is an amplitude cosine of omega t plus p. You could basically describe that waveform with an amplitude, a frequency, and a phase, 3 parameters, instead of giving many, many points on the waveform. And that's sort of what phasers are. And if you compare them to an ideal sinusoid of the same frequency or certain frequency with specific phase, which is the standard for synchrophasers, you can provide a relative phase to that, and that we have called absolute phase or absolute time. Really is a relative phase, but it's relative to a unique convention, which is a waveform that is at peak at the top of the second. And that's a blue trace. That's an ideal 60 hertz waveform with phase of defined as 0. And then any waveform that we sample, we compare with that. So the phase is relative to that, and the amplitude is, of course, for the waveform itself. That's our synchro phaser, if you like. A lot of people in protection are very familiar with phasers. A lot of system studies people are comfortable with phaser domain interactions. So our power system is mostly behaving most of the time. So phasers may be good indication of what the waveform looks like or what's happening, but sometimes it's not quite as easy. Sometimes there are some distortions. I use this waveform, which is including a couple of cycles, and then there is a bit of a switching transient that goes. This is real data from field. So if you see my cursor, the first 2 cycles before the disturbance, that can be well described by a phaser, meaning if I had a phaser, I could reproduce the waveform more or less, with maybe % accuracy or so. But since the disturbance, I can't quite reproduce it by a phaser, a single phaser at least. And that's where synchro waveforms are a lot more valuable because they actually give you a lot more resolution, more of the truth. Data doesn't get lost in that compression. And each have their place. The nice thing with phasers is that they're, less data to communicate relative to waveforms. A lot more data compared to SCADA, but a lot less relative to waveform. And therefore, communication burden and those things are less, especially if you want to send it to far places. But at the end of the day, both synchronized phaser and synchronized waveforms are measurements that have time tagging so that you know where they were done, and they each have their own use. In quasi-steady state, phasers are very good. There's a lot of great applications. In the last 10 years, they have picked up quite a bit in terms of application. The concept is much older than that, but the applications are growing. And waveforms are, again, 2 orders of magnitude more data. Local waveform use has been used forever. All your relays, meters, power quality recorders, these all have been capturing waveforms for a long, long time. Now we are trying to say, what if we could time tag them to microsecond and use multiple measurements at different places that we can compare with each other? So we call them synchronized phase. A couple of other basic definitions. PMUs are well established as phaser measurement units. They're really synchro phaser measurement unit. Otherwise, all relays do measure, but most relays do measure phasers. But we're talking synchro phaser measurement units as PMUs. And not so common, let's call it arbitrary at this time, but maybe over time becomes standard, is a waveform measurement unit, similar to PMU. That's the device or function of another device that basically captures time tag synchronized waveform formation. Moving on, a little bit of a chart to remind people of the measurement domain in traditional power system. Let's say, let's not worry about synchro waveforms per se, or not the fastest the sort of traveling wave measurements, but just the sort of regular power industry measurements to some extent. On the right-hand side, you have got remote terminal units and SCADA type of information. SCADA used to be every 2 seconds, every 10 seconds, your RTU takes a measurement and sends it through your SCADA network to a control center. It may come from thousands of points on your grid. It's usually a phase A to B voltage or something equivalent of that. So it's very low resolution in terms of time, but it covers very wide area, and data arrives at sometimes random time. You don't have good necessarily synchronization between data because they are not time tagged at the source. PMUs come in as phasor measurement units. They're sort of, you could imagine, they're the next generation of the part of SCADA. SCADA is supervisory control and data acquisition. PMUs are the data acquisition side of it. They're not control part of it, of course. There you measure voltage and current, not just voltage, often enough. And the device itself samples at higher frequency, but usually once or maximum twice per cycle is the communication rate or the data rate to provide phasors. There are systems that can do even faster, but often enough with phasors, you're looking at per cycle. It kind of makes sense because the standard focuses on power frequency only, 60 or 50 hertz. And if you go to sub-cycle, well, it is an estimation and it's a fit. Again, you could get it from many points. There are not as many PMUs around as there are RTUs per se, and they would have about 2 orders of magnitude more volume of data because they sample about 100 times more and they send more data, up to 20 parameters, not typically 1. And then as we get closer to substation, the sampling rates and communication rates go up. We have got IEC 6150 sample value merging units with the standard 61869, a standard recommended sampling rates of 4.8 kilohertz or 4.4 kilohertz. 4.8 is for basic metering and protection application. 14.4 is mostly for power quality application. And the communication rate for both of them is about 2400 hertz, meaning you pack 2 measurements or 6 measurements in each packet that you send. That's a recommended value. 3 voltages, 3 currents, or you could say 4 voltages and 4 currents if you also send neutrals. And usually those are sent or subscribed by up to 4 or 5 relays in the substation. So they're not too many endpoints to get data from one merging unit, basically. Then we get to our sort of bit more standard digital relays and meters. They sample at the rate internally they need. In a way, they are the front end of a merging unit, if you like. Relays don't send the measurements out often, only by exception. They send decisions out often enough. And meters typically, again, don't send sort of waveform measurements. They say power and energy measurements, maybe every 5 minutes for some smart meters, things of that kind. But overall, power quality and good quality recorders get to a few tens of kilohertz sampling rate. I've intentionally left also a column empty here. That's a bit more advanced traveling wave relays or some special devices that could sample at megahertz. These are the measurement capability of, I would say, the electronic device. You could always keep in mind, most of these electronic devices get their measurements from instrument transformers, and instrument transformers themselves may have bandwidth limitations, particularly capacity VTs and even potential transformers. They have much narrower bandwidth. CTs have wider bandwidths depending on the load, burden, core size, things like that. Fine for current. But for voltage, transmission PT usually doesn't have a bandwidth more than 2 kilohertz. And CVTs are, of course, very narrow bandwidth. They're resonant tune systems. So even a few 100 hertz You see signals. It's not like you don't see any, but their accuracy is way, way, way off. It could be 10%, 20%. It could be 90% off, basically. But that's a different layer. In the measurement domain, both are important. So between high voltage and low voltage, where the electronics can help, there is the instrument transformer. So in a way, that is a filter that's to block some information. And then there is the device that does the sampling, and that if it's slow or if it doesn't do the job right, that's another filter that can result in loss of information. Let me touch a little bit about a practical element that's very much relevant to utilities. This is not just about measurement, but this applies to synchrophasors, applies to synchro waveforms, applies to any solution introduction into commercial domain, and not just utilities, any domain. I'm sort of looking at a bit of a concept, we call it deep data sensors. These are sensors that you can get a lot of data out of them, depending on what you want to do. And the reason they matter is really more than anything else, the business case, or I call it the practicality of deploying technology. This little chart, which is from a 2017 presentation at the general meeting, shows a cost of deploying technology versus benefits. Often enough, you have a base cost. Let's say the cost of putting sensors on instruments, it's a significant cost, often enough. But you still haven't done anything by just putting sensors. You got to do something with the data you get from the sensors. For example, let's say you put all the instrument transformers, you put all the PMUs in the field, and that's the darker blue cost on the right-hand side here. You still haven't done much, but then you install one software application for situational awareness that reads the PMU data, knows the model of your system or geography, and can tell you, oh, the phases are bad or good, or voltage is too high or too low. That's sort of the benefit. So if you look on the benefit side, the base cost doesn't have a benefit. The application that we install, the function, that's the one that has a benefit. So you have some significant cost to base infrastructure and a little bit cost to that application. On top of that, you could have multiple applications. So the additional applications are usually marginal additional costs because they share the same base cost of the sensors and devices and hardware that were there. But each of them give benefit. In this case, if you had only one application deployed, the overall cost would be higher than the overall benefit. So it's not wise to do it. But if you actually install all four applications, not just situational awareness, but also fault location, voltage stability, transient stability, these are just examples that you could do with PMUs to some extent. If you put all of those, then the values stack up. This is called stacking up values. Collectively now makes business sense. Now you have more value, more benefit than you have cost. You can convince the utility manager, hey, this is a benefit for us. You can convince your utility commission, this is the right thing to do because the investment more than pays off. Yeah? But it's important to have the type of base infrastructure that is in fact provides data that is useful for all these applications. If you needed another base sensors, different type of CTs, different types of phasers to enable another application, then the values couldn't stack up that easily. The cost would be too high. Now, what I wanted to get that and refer that to deep data sensor, these are sensors within voltage and measurement domain that would have wide dynamic range, meaning they measure low currents and high current, low voltage and high voltage with similar accuracy. They have wide frequency response, so they're good for 60 hertz, but they're also good for harmonics and transients and other things, especially with renewables and inverters. You really want to see some of the higher frequency signals. And they have accuracy and linearity basically over this wide dynamic range and that frequency. That makes for a deep data sensor, which both in the dimension of linearity and the dimension of frequency has a lot of capability, can really show what's in the high voltage at the low voltage. And each of these applications can use data, filter everything else out if they want. They can use the data in the domain they're interested. If it's a synchrophaser, may filter only the 60 hertz, right? A different application could look at it differently. let me move on. We'll talk a bit about that because the focus here, one of the emphasis here is that if you do have a deep data sensor with the modernized grid, with the changes we are seeing in our grid, with all the renewables, that is a much more practical investment in the grid because you can use that sensor or that measurement for many, many applications. Often enough, the cost of the crew going to the field putting a sensor is a much higher cost than the cost of equipment itself. So it's really important not to need 5 different type of sensors for 5 different applications. It would be great to have one set of sensors installed and use them for those 5 different applications. One general also a bit of a reminder that synchronized waveforms still considered very young sort of domain. Waveforms are not, synchronized waveforms and their application a bit more. Even synchrophasers are considered relatively young, even though they're coming out of infancy. I would say they're adolescent. They have some good applications. Sometimes they think too much of themselves, synchrophasers, and sometimes they're just right. Now, one thing I want to remind, if you have a synchro waveform device, first of all, you do have a waveform. So everything you could do locally with the waveform or even store data with a waveform, you can still do that with it. So that's a broad brush of application. That's what I call edge application in a way in this case, because at the edge of the grid, wherever you're doing this measurement, you can do all the local applications that you were supposed to do. And sometimes you can do something a little bit more interesting, even at the edge of the grid or centrally, distributed or central. Most of the interesting things but come really when you're talking more than one measurement system to different locations, so that time synchronization, time tagging can help you coordinate or correlate the waveforms and get some good useful information. Phase, power flow, traveling wave, if you have a type of synchro waveform with the right bandwidth and the right speed. But these are more called, I would call them distributed or central application, meaning there is not just measurement, but often enough, there is some level of communication needed to get the data to another place or many other places. And these could be real-time applications or could be non-real-time applications, again, getting data from multiple places. And as a matter of, in terms of waveform resolution, in terms of sampling rate speed, if you like, I want to sort of define 3 categories. One that we call basically slow, which is like synchrophasers. You get the 1 every cycle or 2 every cycle, that sort of level. That almost doesn't fall into the waveform. It's in the phaser domain. It's just 1 or 2 measurements per cycle. It's not enough to really describe a waveform unless it's purely nicely sinusoid. Then you have got the typical, or what you say, medium sort of sampling rate from 1 kilohertz, maybe some older relays, to 10, 20, 30 kilohertz. So these are better quality, higher sampling rate relays, and power quality meters, good quality meters, recorders, and they can help with the harmonic power flow, high impedance fault location, things of that kind. And then you have got some waveforms that you can go to 100 kilohertz to megahertz, okay? Assuming also the instrument transformer has the bandwidth to show faster events. That's the category we got a more faster sampled waveforms. And these help with transients, traveling wave, fault location, things of that kind, even resonances in the circuits in the substation. And just a little bit of illustration here to show what gets lost. To many of you have done digital signal processing, this is obvious, but sometimes we forget that when you sample at higher frequency or lower frequency, at lower frequency you could miss certain things that happens with sampling. This is an actual recorded waveform from the 2 ends of a 25 kilometer roughly line during a fault. So you see a cycle and a half before fault, you see 6 traces. Basically, reds are A and blues are phase B and greens are phase C. The light colors are one side and a darker one are the other side. And we zoom in this case in that little time just at the inception of the fault. This is the fault waveform on just one side, one sort of side of the line, the three phases. This is a B to C kind of fault. You can see the voltages come together. And this is when 6 milliseconds, so a bit less than half a cycle. And it's sampled at 14.4 kilohertz. This is the higher IEC rate so that you can do power quality meter. And that's what the waveform looks like. But if you sample the same thing at megahertz, right? So every 1 microsecond, not every 70 microsecond. You sample, you see this looks quite a bit different. There is some, and if I zoom even in the first 200 microsecond of that, just that little portion, you see actually, oh, there is a specific pattern between green and blue, and these sort of oscillate and get dampened. And in this case, A is picking up some too, but it's much smaller. These are, by the way, electric fields, not voltages. So there is some crosstalk, but that's not the point. The point is really the frequency. And something like here, you see you have got an 8 microsecond, squarish waveform that you completely miss, of course, when you sample at low frequency. The question becomes, so what? What it is good for, what is not. And later you see something like this allows you to locate the fault. This actually 8 microsecond, or is 4 times 2, basically says the fault happened 4 microseconds of traveling wave time away from this terminal, which puts the fault at 1.2 kilometers away from this terminal. It allows you actually to locate the fault within a few tens of meters in this case. But that's the information that's lost in low sampling rate. Want to remind is not just the sampling rate, also the instrument transformer or the sensor should have the bandwidth too, not to filter this sort of information out. A couple of other comments before we jump into more interesting part, which is basically examples. Data quality becomes often enough a big issue when you're in digital domain, whether they're synchrophasors or synchro waveforms. And I want to sort of remind people of their two general categories, and depending on who you're talking to, they could be talking about very different topics. If they're into measurement instruments and relays and devices themselves, you could have been talking about measurement errors, and those are inaccuracies. Maybe your CT has an error, maybe your relay has an error. So you've got basically measurement error, what you're trying to measure voltage and current. In synchronized measurement, you could also have time error. The time tag you're putting on it could be wrong. And then often enough could be a quality information, like synchrophasors, they have a quality status bit, and that could have some wrong things in it, or could be right. Overall, together, all of those give you a trust level in the measurement quality. And there's a lot of metrology effort to get these right, and it's super important. And then you have got the maybe what I call data loss. This is often enough, I call it digital. You either have it or you don't have it. It's not like you're 2% off or 1% error. It's either having data or not. And that could be a break or problem in the measurement instrument, the relay itself, the digital sensor itself could be, broken, could be off, could have a electronic component burn, their input protection burn, something. It could be a data transport issues, and often enough when people talk about data quality issues, they're talking about data transport. They're talking about communication and loss of data in that. And sometimes it's not just loss of data, it's also latency. If you're dealing with real-time applications, if data comes too late, is same as not coming sometimes, right? But for some other applications, latency is not critical. And I want to remind everyone, there's also data storage issues. These days, a lot of those problems are solved with the Googles and AWSs of the world, with triple redundant, diverse storage type of system. But at the end of the day, if you ever had a computer crash on you with a hard drive dead, you know what data storage loss means. So those are there. All of these are important things to address if you want to work with the data from synchro waveforms or synchrophasors for that matter. but data transport seems to causing more loss of hair, I would say, than anything else overall. Now let's jump to a couple of application examples. This is maybe one of the simplest synchro waveform application example. This is a project where a resistive divider at 12 kV, you see them on the sort of left of the pair of the sensors, together with special cabling and together with some digital to analog converter and some software together was used. Resistive dividers, especially depending on their secondary cabling and their ratio, often enough don't have a very wide bandwidth, maybe a few hundred hertz. They're good for power frequency often, and if you're careful, the phase could be okay too. And here the idea was utility wanted, this is close to capacitor switching place, so they were interested in a bit wider performance, seeing switching transients reliably. And basically the idea there was combining a resistive divider, which is usually less expensive, but with some electronics and advanced signal processing and error compensation, and basically produce IEC 6150 sample value at 4.8 kilohertz with decent bandwidth, but decent in this case means about maybe up to 2 kilohertz. But all of these interdependencies and field dependencies made a case for, hey, we think this is good, but we need to basically verify accuracy, calibrate it in the field. For that purpose, they put for a few weeks, actually ended up being a few months, some optical voltage sensors that are optically isolated, is only fiber, is passive up here with electronics at the ground potential, which natively provides sample values, and they're both time tagged, so they can apply the same primary voltage to both sensors. Basically, the optical is the reference, and the other sensor, together with its digitization and everything, is the digital sensor under test. So this is a local synchronized waveform measurement. And in this page, you can see the overlap of the waveforms, the synchronized waveforms. And it's hard to see, the overlap is very good. So the dotted and the not dotted waveforms are from the reference and the device under test. We are also showing in this case the summation of three voltages, or zero sequence if you want to call it. There is significant amount of third harmonic, right? You can see basically about 25% summation of the three, or each of them about, I don't know, 8-9% third harmonic, because it was a feeder that was very, very lightly loaded, and you would expect from the transformer to do have a good amount of third harmonic. But they put that in the field, looked at the accuracy, ratio error, and phase error over some time. It was supposed to be a plus minus 1% system, which after calibration it was and stayed, and plus minus half a degree. But also we were looking at, hey, is its harmonic performance, which is what we really, not we, the people who built the digitization system, tried to compensate for. Again, resistive dividers are not as good with that. Do we still see that? And yeah, the performance was okay. Just keep in mind, this is logarithmic scale on the y-axis. So even if you have a factor of 2 differences, 100% differences, it's really hard to see. They almost overlap fairly well. But it also shows that you have a, order of 4 dynamic range here in terms of looking at this signal. That was one application. They also verified that weighted enough to see a switching transient on both sensors and say, yeah, you could get the switching transients they were looking for. Of course, this was only 4.8 kilohertz, so by nature, this should be a little bit filtered, but that was good. Let's jump to what's a bit closer to heart for me, and it's a bit higher frequency, a higher resolution. And that's sort of a bit of event comparison. You see a disturbance. Again, this is more like a switching signal. This is a megahertz sampling optical sensor with about 200 kilohertz bandwidth. Remember, the sampling rate and bandwidth are 2 different things. 3 dB bandwidth is often, where you could see a signal with certain level of accuracy. 3 dB means half power. Sampling rate could be very high, but bandwidth could be very low. But at the end of the day, we know bandwidth can never be more than half of sampling rate. That's Nyquist criteria. So you're sampling in megahertz, you do not have a chance of seeing anything more than 500 hertz signal. Otherwise, it aliases. Anyways, this is synchronized measurements at the two ends of the line. You can see a transient arriving, you know, the light blue and dark blue again are the two ends, B phase, or you can look at A phase. They have different intensity, but the distortion, you can see they're 121 microsecond time difference. This line, by the way, if the traveling wave or if the disturbance had started at one substation from previous measurements, we know it takes about 204 microsecond to get to the other end. So we know since this time is less, the event must have happened somewhere in the line, you know, not in the middle. If it was in the middle of the line, would arrive at the two ends at the exact same time. So the time difference would be 0. But this basically allows an event location, whatever disturbance caused this, whether it was a switching, arcing, something that happened, you know, based on this 121, we can locate what location on the line it was. Same thing, let's look at it with a fault. Here is a fault. We look at that early part of the fault and zoom in quite a bit right at that transient. And this shows basically there was a fault on B phase. You know, the time difference between the traveling wave arrival at the two terminals, the two ends of the line, is 62 microseconds. For this particular line, we knew the line was about 80 microseconds long, meaning a traveling wave takes 80 microseconds going. For those of you who are not as familiar with traveling wave, in a simplified way, not getting into modes and details, a traveling wave, when a change happens on the line, that travels to the two end. That's like a step function. That travels in both directions along the line, or all directions, I should say. And basically, the travel speed depends on the dielectric constant of the medium. For overhead transmission lines, that's mostly air, which basically this wave travels very close to speed of light, okay? Which, you know, the scientists say 3 times 10 to the power 8 meters per second. The engineer and me says that's 300 meters per microsecond. So that wave is traveling, it's the same thing, it's just a different way of expressing it. But if I sample every microsecond, okay, I have the ability to say when the wave arrived, and within a microsecond resolution. If, let's say, in this case, let's say if it takes 80 microseconds for wave to travel the line length is 80 times 300, which is 24 kilometers. This is a 24 kilometer line, and it takes traveling wave to travel one end to the other end 80 microseconds. When the time difference between the wave arrivals at the two ends is 62, that tells me, so the fault must have happened at 9 microseconds from one side and 71 microseconds from the other one. 9 and 71. Together, that's the 80 microsecond, okay? And their difference between 9 and 71 is 62, right? So if a fault happened at that point at 9 versus 71, so 9/80th, or about 11% of the line length is where the fault happened. You know, 11% from the terminal that shows it first, and of course, 89% of the length of the line from that. So this can give you accurate fault location, but if you sample at the microsecond, you have 300 meters resolution, or when you look at it differentially, 150 microsecond. So this technique can allow you to locate the fault on a long transmission line within 150 meters or 500 feet, depending on what units you're more comfortable with. That's basically nicely within the tower. That's fairly accurate fault location. But if you didn't sample at the microsecond and didn't have bandwidth, if you sampled at 100 kilohertz, so every 10 microsecond, then you wouldn't know it within 300 meters, you would know it within 3 kilometers, which is not very nice. And even 100 kilohertz is considered fast sampling. Most relays don't do more than 10 kilohertz. And if they try traveling wave, they would show the fault within 30 kilometers. Well, that's not very useful. You know, many lines are not even 30 kilometers themselves, like in this case. right? So information like this with a regular recorder or regular relay is lost. You need something with high speed. This is an application of high resolution synchro waveforms arriving at the central place in this case, or they could just exchange with each other, but arriving a central place from the two synchro waveform measurements at the two ends of this line. They're actually really one in each of the substation. This is voltage or electric field based measurement. So all the lines coming to a substation can be represented or can be monitored with one measurement device. And this is another one. I sort of zoom in. This is similar or actually the same waveform I showed earlier about losing information. You can see that, oh, there's 72 microsecond time difference between arriving at one end versus the other one. Let's say it's the same line with 80 microsecond total line length. With the 72 microsecond time difference, I'm going from light green to the dark green transitions. That says it's 4 microseconds from one end and 76 microseconds from the other end. And 4 microseconds travels times 300 meters is about 1.2 kilometers. What's interesting here is, see this green, and this particular terminal of the line is a normally open terminal. So when a fault happens, traveling wave comes, hits the open terminal, reflects, in a way doubles and reflects, hits the short circuit again, reverses and comes back and reflects, hits the short circuit, reverses again. So every time it hits the short circuit, it reverses polarity. Every time it hits the open end of the line, it just reflects, it doubles and reflects. So you see a reflection pattern. Every 8 microsecond, a wave arrives at this terminal, which is, the first one is the first wave that arrives. We don't necessarily know when it left its fault location, but then we see, oh, another reversing wave arrived about 8 microseconds later. The nice thing here is that you can go ahead and count and say, oh, 10 of these happen in 82 microseconds. So every one of these reflection is not actually 8, it's 8.2. You get even finer resolution than your microsecond sampling. Oh, if it's 8.2, that means the time to travel from the fault to the terminal and back is 8.2. So the distance is 4.1, half of that. And 4.1 times 300 meters, oh, the fault is at 1,230 meters, right? So you get to 1.23, not just 1.2. You get an order of magnitude better resolution. It's not within, in this case, it's not within 300 meters, it's within 30 meters, you're confident where the fault is. This is a special case, but when you see these patterns, you can take that sort of information out of it. This is purely an example of accurate fault location, right? Here's a completely different example. We had a slow and a fast. Let's go back to the slow waveforms. This is closer to basically renewable facility. A power quality meter is tracking total harmonic distortion over time. See, the time is in minutes. This is a lot of time. This is not a waveform. But you see, total harmonic distortion jumps up a little bit here and jumps up a little bit here, okay? Or if you look at the change in total harmonic distortion, there is a big step here and it's a good step here. And that kind of implies, if your total harmonic distortion has increased, that kind of implies there is a disturbance in the waveform. If your waveform was perfectly purely 60 hertz or 50 hertz and no noise, your total harmonic distortion would be 0, okay? With some noise and some harmonics, you have some base total harmonic distortion, okay? But when you have a little step up in a short time, usually means a waveform disturbance. If you look at the waveform for this particular example, you see there is a waveform and then there is some form of switching-like disturbance on it, okay? And one of the ways that this is from Dr. Mohseni and Rod's research together with Dr. Wilson Chu. One of the ways is they're trying to qualify and identify those disturbances. This is called the event waveform. which is basically if you take the actual waveform and subtract the previous cycle in a way, the non-disturbed waveform. This looks at different. Pay attention here, the x-axis here is plus minus 600 volt, here is plus minus 200 volts. So basically this disturbance is zoomed up. It's a factor of 3 zoomed up. So superposition of this event waveform on top of the regular 60 hertz signal in this case makes for the real waveform. And getting these waveforms may allow you to find patterns. For example, these are event waveforms. Maybe these inverters, when they switch, when they operate, they create these sort of waveforms. You could get pattern recognition. You can get them to clustering techniques to look at, hey, these sort of problems. If you have it only on 1 or 2 inverter, no big deal. But if a lot of inverters in your system have this issue together, that could affect your power quality on the grid or could initiate other stuff. Here's a more of the same thing in a synchronized waveform environment. 2 waveform measurement units. These are low frequency waveform measurement units, just like these ones, only a few kilohertz, not megahertz ones. Let's call it regular power quality meter. Connected to 2 69 kV terminals at 2 different substations. And if you look at those, and if they are synchronized measurements, you can see something happened here that the equivalent of that didn't happen here or wasn't that size. So that's a local event. But you see something happen here in terms of signal distortion that you see that both location and an exact same time and somewhat, similar in terms of orders of magnitude. Say, this is not a local, that's a sort of grid event issue or something that is common between the 2 sites. That allows you for a lot more root cause analysis, event analysis if something happens, especially if you do, in addition to total harmonic distortion, do capture the wavelets and waveforms and see what similarities they have. I stopped there. There is, again, as I said, this whole thing is fairly early in its introduction. The traveling wave was a neat, simple use case. Same type of measurement can allow you to go after grid analysis, transformer analysis, all sort of events when you have that higher resolution and synchronized information. And I'll pause and maybe I'll go out of the presentation mode. And,
no, gente, pueden hacer preguntas en español o inglés. Creo que estamos en un ambiente controlado y pueden optar por usar el chat, usar el español, el inglés. Si hacen directamente la pregunta en inglés, la va a escuchar Farnoosh, y si no se entiende muy bien, tenemos a María Julia que nos va a ayudar. Adelante, acá hay mucha gente que sabe de esto.
Go ahead, Pablo.
Hi, thanks, Farnoosh, for your talk. I would like to ask these synchronized waveforms. Do you have some examples applying these concepts to voltage stability or transient stability?
I haven't done that as much. I know of some of my colleagues that they have tried to look at synchrophasors for voltage stability. Phasors maybe depends if you're looking at transmission system. So with voltage stability being a little bit slower sort of process, typically they think synchrophasors are sufficient. But Dr. Mohsin Inrad and a couple of other researchers I know, they are looking at synchro waveforms and maybe use in transient stability as well as voltage stability at distribution level, which the events could be possibly faster. I haven't done anything myself, or I'm not directly aware of that.
Okay, thanks. I was concerned because the transient stability and voltage stability, you have usually more time to act. So there may be no gain from switching from synchrophasors to synchro waveforms.
Yeah. for that reason, that hasn't been the priority. Maybe there is some more information there, but general idea is that, as you said, there is more time, so it's a slower process. So quasi steady state information you get from phaser probably is sufficient. Probably.
Yes, maybe if there are a lot of inverters, you have solar panels in the
Yes.
at the distribution level. I think that there is a possibility to use this.
There is, and part of it, part of the whole discussion is if you're not seeing things, okay, you don't have a chance, right? You don't have when you don't see things, when you don't have the bandwidth or the sampling rate, and faster events happen. They may not be important, or they may be important. When you don't see them, you don't have a chance. If you see
Sure.
them, yeah, when you see them, you have the door open, and you know, sometimes we zoom on them and say, yeah, we see these and no big deal, no problem. You know, we see harmonics, for example, with inverters at 7-8 kilohertz with these sensors because they have very wide bandwidth. But you see that, oh, it's in less than 1% of 1%, okay, or you know, less than 1 in 1,000 compared to primary. So it is there, but it's small and it's okay. And that's good to have that confidence that, oh, you know, the inverter is working properly. For example, it is, you know, switching time is correct, so you're not creating big harmonics. And it's also confidence that, oh, in case it doesn't, and these harmonics grow, you can see it. But at the end of the day, it comes down to we are putting a lot more on our grid, active devices, and also we are getting a lot more hit from the environment with climate change, with weather events. If we have the ability to see the grid better, we have a better chance to do all the controls, all the active or reactive effort that we need to do to keep the grid and power on.
Okay, thanks.
Sure. Any other questions?
Please. As you know, Dr. Farnoosh, here in Uruguay, we have installed a rush system, and we use the synchrophraxos visors, and we have stations, I don't remember the amount, but about 15. The people here can help me. And we are beginning, well, the last years, beginning to use that data. And also we installed a RAS system that decides to disconnect part of the systems. But I'm talking by people that they are here and they know more than me. I only a user of that.
It's separate from sometimes a few utilities or a few ISOs we have seen that they are having PMUs in a more functional role, RAS systems with sometimes PMUs, sometimes limited PMUs and special relays doing RAS schemes. But some of these synchronized waveform system at a few key points on the grid, it also provides a very good monitoring and understanding of learning of the events for future. So what happens, you know, a lot of those are based on a lot of system models and understanding, and they work overall well. But in the engineering work, we know nothing is perfect. Everything has some limitations. And if you have a level of visibility and monitoring with high resolution, good time synchronization, and independent of the RAS scheme and independent of operating system, just monitoring, just observing, that can give very useful information sometimes to, you know, validate models, fine-tune models, make sure communication worked right, timing of the breakers, switching on, switching off, those were all accurate. So we're getting people really looking at another layer, high resolution, but less criticality because it's only monitoring. We're seeing a good interest in that, so that the grid and the actions we take are better understood, and the consequences of actions are also better understood.
Someone, another question?
Sure.
Yes, I have a question. Hi, Dr. Farnoosh. Hi, everyone. Thank you, Doctor, for your presentation. It was very interesting and very, very clear. I have a doubt without that you mentioned before about the THD, the use of THD in order to identify an event in the grid. And the question is if in this case you have used a THD with high order harmonics. Because in the case of THD, the order of the harmonic is limited up to 50.
If you go by standard, yes, correct. You're right. Yeah, and that's no, the example you saw here is these are standard power quality meters actually. Okay.
Okay.
Which also have waveform, so they only look at those. But if you use a device like this, okay, that has megahertz capability, and look at true THD, well, true to its bandwidth, then that's different. You're exactly right. If you use THD, you're limited by the definition of that particular THD, that particular device. Most relays, most devices are designed with anti-alias filtering for good reason, to filter out anything really high frequency and only look at the few harmonics that the standard asks them to look at. And if you're looking at inverter behavior, you actually don't want just the standard THD. You really want the true THD. True within the bandwidth of the device. But a device like this one has a 200 kilohertz bandwidth and shows anything, all the THD up to 200 kilohertz. But a device that gives something like this most likely has a 5 kilohertz bandwidth and goes by the standard and filters everything out. So you effectively have a 3 kilohertz bandwidth for your THD, not a 200 kilohertz bandwidth. So that's a big difference. And past events, a lightning impulse doesn't affect this THD, but a lightning impulse will be captured by THD from this system. And by the way, THD just total harmonic distortion, in case anybody else is wondering.
Okay, doctor, you have two questions in the chat. Is possible you see that, or I read to you?
I can see it. It says, okay, what kind of sensor you need to capture the data? It depends what you want to do. So for these fault locations, you do need a very wideband sensor. So in our case, we are a bit biased as an organization. We focus on wideband optical sensors, but you could have a special CR dividers if you can put them in the field. At least for the lab, they're good. Or CTs, special types of current transformers, if you're looking at current and not voltage, could have that sort of bandwidth. And then, of course, your electronics got to have the sampling rate and filtering element. But in our case, we like the safety and isolation of optical and the nice bandwidth they have. So we focus on that. And only optical or resistive sensors. No, so for megahertz sampling, definitely not resistive. Resistive sensors and the secondary wiring do not have the bandwidth. Even in kilohertz, they have a very hard time. Like most resistive dividers, even at distribution, by the time you pass 200, 300, 400 hertz, you have significant error in terms of ratio. The lower the output of the resistive dividers, and if they're of special non-inductive type, they can give you more bandwidth. But most typical cheaper outdoor resistive dividers are not those special nice low inductance types. So, and by the time you get to a few kilohertz, yeah, no, resistive dividers are not there. You could have RC dividers, resistive capacitive, which are more lab and slowly coming to the field. And by the time you get to a few tens of kilohertz, even they have a hard time. But these particular waveforms are from optics. So I saw those two questions, hoping, Marcelo, I hope that was a sufficient answer.
Okay, and for it's good that Nyquist is still there, no?
Yep, Nyquist
yeah.
there. And you can.
But what about the amount of data that you receive? This needed a clusterization of the information because
Correct,
really.
correct. So we apply with the project, with the people we work, we try to apply. So again, these particular sensors, for example, they do have synchrophasor output, which is like any other PMU streaming out, you know, people can use it or not. There is sample value output, which again, like any merging unit, people can hook it up to a relay, not too far, right? Usually it's within the substation. But the high resolution megahertz data, even though the sensor is sampling all the time, is not usually streamed all the time. So there are triggers in the device, and when something anomaly happens, either a fast change of voltage or amplitude drop, you know, voltage sag, voltage swell, significant frequency change, some trigger, and then it captures waveform relative to that event. And for example, this particular waveform you see and the device, it's set up that if a fault like this happens, it captures 6 cycles before and minimum 9 cycles after. So that's about 250 milliseconds, a quarter of a second. Megahertz data, 3-phase, you have that high resolution. At the same time, samples 14.4 kilohertz, like the standard power quality rate, 1 second before and 15 seconds after. So lower sampling rate, but wider window. And also samples PMU data 4 minutes before and 10 minutes after for every event. So you do get a correlation of what were the very tight fasting happening around that, which most of them decay and die off within milliseconds, right? So they're not as relevant maybe 10 minutes later. And then again, slower waveform sampling, wider time range, and then PMUs or phasers wider, or continuous, but at least wider. That allows you to manage with priority the volume of data. You're right, the data can become very large, very fast if you were sampling at this rate and keeping everything.
Okay. More questions? If we don't have more questions, we are in the end of the webinar. I want to thanks again to Dr. Farnoosh. Excuse me.
I see one hand up.
Who is?
It's me.
I don't see.
I'm going to turn on my camera. Hello.
Oh, yes.
Okay.
First of all, thank you. Thank you very much for the presentation and for being here with us today. Actually, my question is not strictly related to the most technical aspects here because I am an undergraduate student, so I honestly couldn't grasp the whole of the technical aspect that you discussed. But anyway, I wanted to thank you because I think that this presentation and this chance is a really good opportunity for us undergraduates to see what it's like to work in the research world, let's say. And I also wanted to ask you, as a person who is willing, I am in my 3rd year of the career, and I would like to specialize in sustainable energies and power electronics in the future. So I wanted to ask you if you could give some advice for students like us who like to work and dedicate our career to that field.
That is actually a great domain and very much in demand. You know, one of the elements within PES, we're really trying to encourage, not just at an undergrad. I think we got to reach to grade 6, grade 7. At that age, with high school or early high school, to encourage people that, hey, if climate change, if the environment is important, and for a lot of people is, this is one of the best ways you can have a career that can actually impact and help. Okay? And they're both sides of it. There is renewable integration, which again, power electronics, as you mentioned, is a big, big topic of it. Not just power electronic itself, but also what comes out of it, the impact of it. How do you integrate that safely and reliably with the grid? How do you do all the good deed without damaging the grid? Because that's very important. And the other side of resiliency is also, some of these waveforms and information helps with that renewable, but this sort of technical ability also allows you to monitor the grid, react to the problems that may arise very quickly. So fast control loops. I mean, if you do that field, go after power electronics and things, you'll see that it's all about controls. Like that's one of the core fundamental fields in our area. I think some of our good researchers that are active in controls probably could tell you about that too. That applies to many aspects of it, but it's a very, very promising, a lot of potential. I mean, it's a great time to be a student picking a field. And this is a very hot topic, but both sides of it, both the side of the power electronics and the part of the grid, which is gonna be interacted and sort of interrelated with the large amount of power electronics. So definitely go for it. It's a very exciting field, a lot of room for growth from all aspects.
Very
The future
good.
is power electronics, be sure. All the energy pass through power electronics. I'm teacher of power electronics.
We'll go for it then. Thank you very much. Really, thanks.
Another one? Well, if we have no questions, thanks again, Dr. Farnoosh. Really, we enjoyed the presentation. It was very clear, and I'm sure it's going to be useful for all the people that share with us this moment. And thank you, really, thank you. We are going to try to put this video in our website, and also we are going to inform the people that were